Right now, as you are listening to this, something deeply abnormal is unfolding beneath the surface of the United States. Reservoirs across the Southwest are collapsing toward critical thresholds months earlier than expected. Soil moisture across enormous sections of the Great Plains has already fallen to levels scientists normally associate with the peak of late summer. Snowpack throughout parts of the Rocky Mountains and Sierra Nevada melted so early this year that some river systems entered stress conditions before the world notice. Hottest part of the season even arrived. And according to a growing body of climate research, the drought itself may not actually be the disaster. It may only be the opening stage of something much larger now beginning to organize across the atmosphere of North America. Something capable of reshaping agriculture, water security, wildfire behavior, energy infrastructure, food prices, migration patterns, and even the long-term stability of entire ecosystems over the coming decades. Because the terrifying reality is this: the worst drought in modern American history may have only been the beginning. And what comes after the beginning is what has climate scientists increasingly concerned behind closed doors. Tonight, we journey deep into the terrifying scientific reality behind the expanding megadrought, the collapse of western snowpack, the amplification of heat domes, atmospheric instability, vapor pressure deficit, wildfire escalation, and the growing climate feedback loops now reshaping the United States in real time. And if you live anywhere in America, this story is about you. It does not matter whether you are in California, Texas, Arizona, Colorado, Florida, the Midwest, because the atmosphere above North America no longer behaves like a collection of isolated regional weather systems. The continent is increasingly operating as one connected climate engine, where drought in the Southwest influences food production in the Midwest, where wildfire smoke from Canada darkens skies over New York, and where warming oceans thousands of miles away can alter the jet stream directly above your home. The reason you need to keep listening tonight is because most people still do not understand what is actually happening underneath the headlines. The media usually treats heat waves, droughts, floods, wildfires, collapsing reservoirs, crop failures, and smoke events as separate disasters. But scientists now increasingly understand they are not separate at all. They are symptoms of one larger atmospheric transition now accelerating across the planet in real time. And once you see the hidden system connecting them together, it becomes impossible to unsee. So if this kind of deep atmospheric storytelling helps you relax, think, or simply better understand the strange century we now find ourselves living through, consider quietly leaving a like on the video so this journey can reach more people searching for answers beneath all the noise and uncertainty. And stay with me tonight, because one of the most disturbing discoveries in modern climate science is not simply that the planet is warming. It is that warming itself may now be activating self-reinforcing feedback loops capable of pushing future extremes far beyond what historical records alone will predict. Over the course of this journey, we will explore the hidden mechanics behind vapor pressure deficit, why the western fire season is rapidly expanding, how atmospheric blocking patterns are beginning to stall over North America, why heat domes are becoming more persistent, how drought changes the biological structure of entire landscapes, and why some climate researchers quietly fear that modern civilization may already be entering environmental conditions it was never designed to operate inside. Because the drought was never the full story. The drought was simply the first visible crack in a much larger system now beginning to destabilize. What makes this situation so unsettling is not simply the heat, or the drought, or even the fires themselves. It is the growing realization that the atmosphere above the northern hemisphere may no longer be moving the way it used to be. Because one of the most alarming discoveries emerging from modern climate science is that large sections of Earth's atmospheric circulation appear to be slowing down, stalling, and locking into place for longer periods of time than historical records would normally predict. And once an atmosphere begins to stall, entire continents can become trapped beneath the same weather pattern for weeks at a time. Heat domes linger. Drought intensifies. Rainfall disappears. Reservoirs collapse. Crops fail. Wildfires multiply. And the land below slowly begins to dry out faster than natural systems can recover. Scientists have started noticing this pattern more frequently across North America over the last 2 decades. Massive high-pressure systems now routinely park themselves over the western United States for extended periods, compressing air downward toward the surface, heating the atmosphere, suppressing cloud formation, and preventing meaningful rainfall from entering already stressed regions. These stalled atmospheric structures are known as blocking patterns, and they are becoming one of the defining features of modern climate instability. To understand why this matters so much, you first have to understand how Earth normally redistributes heat. The planet constantly tries to balance temperature differences between the equator and the poles through massive rivers of air moving high above the surface, called jet streams. These jet streams normally oscillate in large waves across the northern hemisphere, carrying storms, moisture, and temperature changes from west to east. Historically, this movement prevented any single weather regime from remaining stationary for too long. But in recent years, researchers have observed something unusual beginning to happen. The jet stream itself appears to be weakening and becoming more distorted. Instead of flowing quickly around the hemisphere, it increasingly develops large looping waves that move more slowly and sometimes become nearly stationary. And when these waves stall, the consequences underneath them can become catastrophic. A stalled ridge of high pressure creates heat domes. A stalled trough creates prolonged flooding and storm outbreaks. In both cases, the atmosphere essentially becomes trapped. Some climatologists believe one major driver behind this behavior is the rapidly warming Arctic. The Arctic is heating nearly 4 times faster than the global average, a phenomenon known as Arctic amplification. As the temperature difference between the polar regions and the equator decreases, the jet stream loses part of the energy gradient that historically kept it moving quickly and efficiently. The result may be a weaker, slower, more unstable atmospheric circulation system capable of producing longer-lasting extremes across the mid-latitude, including the United States. And once these blocking patterns established themselves over drought regions, they created a devastating feedback loop. Dry soil heats faster than moist soil because there is less water available for evaporation. Hotter land then heats the air above it more efficiently, strengthening the high-pressure ridge even further. The stronger ridge suppresses more rainfall, which dries the soil even more, which intensifies the heat again. The atmosphere and the land begin amplifying each other simultaneously. This is one reason modern heat waves are becoming so much more dangerous than historical heat waves. They are no longer isolated weather events. They are increasingly self-reinforcing climate systems. During the summer of 2021, parts of the Pacific Northwest experienced temperatures so extreme that entire towns shattered historical records by margins scientists once considered statistically impossible. The town of Lytton in British Columbia reached nearly 122 degrees Fahrenheit before being almost completely destroyed by wildfire the following day. Researchers studying the event concluded that the probability of such temperatures occurring without long-term climate warming was extraordinarily low. And what frightened many atmospheric scientists was not only the heat itself, but the structures surrounding it. The heat dome became trapped beneath an unusually amplified blocking pattern that prevented the atmosphere from releasing accumulated heat for days. Similar patterns have since appeared repeatedly across North America, Europe, and Asia. The atmosphere is not simply warming. It is becoming less stable, less predictable, and in some cases more persistent in its extremes. And that persistence may be the most dangerous part of all. Because ecosystems, agriculture, reservoirs, power grids, and even human bodies are often incapable of surviving short-term stress. What becomes catastrophic is prolonged stress without recovery. A single hot week and damaged crops. A month-long heat dome can destroy entire growing seasons. A single dry season can strain reservoirs. Multiple years of atmospheric blocking can permanently alter water systems across entire regions. And tonight, scientists are increasingly worried that the western United States may now be entering exactly that kind of prolonged atmospheric regime. Long before the first wildfire ignites, before reservoirs begin falling toward emergency levels, and before entire valleys disappear beneath heat and smoke, The real warning signs often begin thousands of feet above sea level in silence. Hidden deep within the mountains of the American West, the snow itself has started behaving differently. And according to hydrologists across the western United States, this may be one of the clearest signals that the continent's water system is entering dangerous territory. Because the snowpack of the Sierra Nevada, the Cascades, and the Rocky Mountains does far more than create winter scenery. It functions as one of the largest natural freshwater storage systems in North America. Every winter, storms deposit enormous amounts of snow across the high elevations. That snow slowly melts throughout spring and summer, feeding rivers, replenishing groundwater, stabilizing ecosystems, supporting agriculture, and providing drinking water for tens of millions of people. Historically, this gradual melt acted like a natural timing mechanism for the entire Western water cycle. But now, that timing mechanism is beginning to break. In recent decades, scientists have documented a dramatic decline in both snowpack depth and snowpack duration across much of the western United States. Warmer winters increasingly cause precipitation to fall as rain instead of snow. Snow that does accumulate melts earlier in the season due to rising spring temperatures. In some regions, peak snowpack now arrives weeks earlier than historical averages, shortening the period during which mountains can store water naturally. This creates a cascading problem for the entire region below. When snow melts too early, rivers experience stronger flow during late winter and early spring, but far less water remains available during the hottest months of summer when demand is highest. Reservoir systems designed around 20th century melt patterns suddenly receive water at the wrong time. Soil dries earlier. Vegetation cures earlier. Fire season expands. Agriculture becomes more vulnerable. And the atmosphere above these drying landscapes begins heating more aggressively as evaporation declines. The Colorado River Basin provides one of the clearest examples of this transformation. The river system supplies water to approximately 40 million people across 7 states, including major cities like Las Vegas, Phoenix, Los Angeles, Denver, and San Diego. Yet the river's flow has been steadily declining for decades. Scientists estimate that warming temperatures alone have already reduced Colorado River flow by roughly 20% compared to historical averages. Much of this decline traces directly back to snowpack loss and increased evaporation throughout the basin. And the terrifying reality is that many current water systems were never designed for this kind of climate. Most Western infrastructure was engineered during an unusually wet period in 20th century American history. Reservoir capacities, agricultural planning, interstate water agreements, and hydroelectric systems all assumed the climate stability of the past would continue into the future. But that assumption is now collapsing. Lake Mead and Lake Powell, the 2 largest reservoirs in the United States, have both spent recent years approaching historically low levels. Massive white mineral rings now surround their shorelines like visible scars marking where water once stood. Hydrologists sometimes refer to these exposed reservoir walls as bathtub rings, but from space they look less like rings and more like warnings. Because once reservoirs fall below certain thresholds, consequences begin multiplying rapidly. Hydroelectric production declines. Water restrictions intensify. Agricultural allocations shrink. Groundwater pumping accelerates. Soil degradation increases. Entire regional economies begin operating under stress. And unlike many short-term disasters, drought compounds over time. Every dry year weakens the system further before the next dry year arrives. This is why some researchers now describe the American West as entering a state of aridification rather than temporary drought. Drought implies something abnormal that eventually ends. Aridification implies a long-term transition toward a drier baseline climate itself. And this distinction changes everything. Because if the baseline climate is shifting permanently, then the historical record may no longer provide reliable guidance for the future. The water systems modern America depends upon may increasingly find themselves operating inside conditions they were never built to survive. The mountains are still producing snow. Rivers still flow. Reservoirs still hold water. But the hidden timing system underneath all of it is beginning to destabilize. And as that timing system breaks down, the consequences spread outward across agriculture, cities, ecosystems, energy systems, and eventually the atmosphere itself. There's a scientific term that almost nobody outside climate research has ever heard of, yet it may explain more about modern wildfire behavior than nearly any other variable currently being studied. It is called vapor pressure deficit. And once scientists began fully understanding its implications, many realized they were looking at one of the hidden engines driving the explosive escalation of drought, heat waves, and megafires across the Western world. Vapor pressure deficit sounds technical and abstract, but the concept itself is surprisingly simple. It measures how thirsty the atmosphere is. More specifically, it measures the difference between how much moisture the air currently contains and how much moisture the air could potentially hold before becoming saturated. The larger this gap becomes, the more aggressively the atmosphere pulls water out of everything it touches. Soil, forests, crops, rivers, even living plants themselves. And this is where warming becomes especially dangerous. Warmer air can hold exponentially more water vapor than cooler air. As temperatures rise, the atmosphere's capacity for moisture increases rapidly. But unless actual moisture increases at the same pace, the deficit widens. The atmosphere becomes thirst-IER. And a thirst-IER atmosphere extracts water from landscapes with increasing intensity. Scientists sometimes describe this process as the atmosphere acting like a giant invisible sponge. The hotter the atmosphere becomes, the harder that sponge pulls moisture upward from the surface below. This is one reason modern droughts behave differently from many historical droughts. In the past, drought often meant lack of rainfall alone. Today, even when precipitation remains near average in some regions, rising temperatures can still intensify drying because the atmosphere itself removes moisture more efficiently. The land loses water faster than natural systems can replace it. Forests become stressed. Vegetation weakens. Fuel moisture collapses. And wildfire risk rises dramatically. Researchers studying wildfire behavior across the western United States have found remarkably strong relationships between vapor pressure deficit and total burned area. In some analyses, vapor pressure deficit explains fire expansion more effectively than precipitation alone. This is because wildfires are not simply controlled by how much rain falls. They are controlled by how dry the fuel becomes afterward. And vapor pressure deficit directly governs how quickly landscapes lose that moisture. During periods of extremely high atmospheric thirst, forests can rise to dangerous levels with astonishing speed. A healthy landscape can suddenly become flammable weeks earlier than expected. Entire ecosystems become biologically stressed. Trees close microscopic pores called stomata in an attempt to conserve water, reducing photosynthesis and slowing growth. Some trees eventually die from hydraulic failure, essentially losing the ability to transport water internally. Others become weakened and vulnerable to insect infestations, particularly bark beetles, which have devastated millions of acres of western forests in recent decades. These dead forests then become enormous fuel reservoirs waiting for ignition. Then once fires begin under high vapor pressure deficit conditions, the atmosphere itself actively intensifies combustion. Flames burn hotter. Fuels ignite more easily. Fires spread faster. Smoke plumes rise higher into the atmosphere. In extreme cases, wildfires can even begin generating their own weather systems, producing pyrocumulus clouds and fire-driven winds capable of creating terrifying feedback loops inside the blaze itself. Some researchers now believe vapor pressure deficit may be one of the clearest fingerprints of long-term climate warming visible in wildfire behavior. Because unlike rainfall patterns, which naturally fluctuate year to year to year to year, atmospheric thirst has shown strong upward trends across much of the western United States over recent decades. The atmosphere is not simply warmer than it used to be. It is more aggressively extractive, more demanding, more biologically stressful. And this subtle shift may be quietly transforming the relationship between climate and fire across entire continents. The terrifying part is that vapor pressure deficit does not require record-breaking temperatures to become dangerous. Even moderately above average heat can produce severe drying if humidity remains low long enough. This means regions can experience extreme fire danger without necessarily experiencing the hottest temperatures in recorded history. The atmosphere slowly dries the landscape day after day until ecosystems cross invisible biological thresholds. And once those thresholds are crossed, ignition becomes far easier than most people realize. A single spark, the power line, a lightning strike, a piece of machinery. Under the wrong atmospheric conditions, that is all it takes. The most dangerous part of modern heat is not simply that temperatures are rising. It is that the atmosphere is beginning to trap that heat for longer periods of time. Across the United States, scientists are observing the increasing formation of massive high-pressure systems, known as heat domes. Atmospheric structures capable of locking entire regions beneath relentless heat for days or even weeks. And these systems are becoming one of the defining signatures of 21st century climate instability. A heat dome forms when a strong area of high pressure settles over a region and begins compressing air downward toward the surface. As the air sinks, it warms through compression, suppresses cloud formation, blocks rainfall, and traps heat underneath like a giant invisible lid placed over the landscape. The longer the dome remains stationary, the hotter the ground becomes. Soil dries out. Vegetation loses moisture. Rivers shrink. Cities absorb solar radiation faster than they can release it overnight. And once the land itself becomes dry enough, the heat dome begins amplifying itself. Dry ground heats more aggressively than moist ground because less energy is spent on evaporation. This additional heating strengthens the atmosphere above it, reinforcing the high-pressure system even further. The system becomes a feedback loop. The heat strengthens the dome, and the dome intensifies the heat. Scientists increasingly believe this is why modern heat waves are behaving differently from many historical heat waves. In previous decades, hot periods often passed relatively quickly as weather systems continued moving across the continent. But modern heat domes are becoming more persistent. Some atmospheric researchers suspect weakening jet stream flow may partially contribute to this persistence by allowing blocking patterns to stall over regions for longer periods. Once trapped beneath these stalled ridges, entire states can experience prolonged atmospheric stress without meaningful recovery. During the 2021 Pacific Northwest heatwave, temperatures reached levels that shattered historical records by astonishing margins. Portland reached 116 degrees Fahrenheit. Seattle climbed above 108 degrees. Roads buckled. Electrical infrastructure strained. Hundreds of excess deaths were later associated with the event. But what deeply unsettled scientists was not simply the magnitude of the temperatures. It was how statistically extreme the event appeared compared to the historical climate record. Some researchers concluded the heatwave would have been virtually impossible without long trends already reshaping atmospheric behavior. And as ocean temperatures continue rising globally, heat domes may become even more dangerous in the decades ahead. Warmer oceans inject additional energy and moisture into the atmosphere, altering pressure gradients and atmospheric circulation patterns across the northern hemisphere. This creates conditions increasingly favorable for persistent ridges, amplified blocking patterns, and prolonged heat events. The terrifying reality is that modern civilization was largely built during a relatively stable climatic period. Agriculture, power grids, water systems, transportation infrastructure, and urban design all evolved around assumptions about historical weather boundaries. But heat domes are beginning to push beyond those boundaries. And unlike many natural disasters, heatwaves often kill silently. There are no collapsing buildings or visible storm surges. Instead, electrical systems fail. Crops wither. Water demand surges. Hospitals fill slowly. Ecosystems dry out under sustained thermal stress. And after enough consecutive days beneath extreme heat, entire landscapes become biologically exhausted. The western United States may now be entering exactly this kind of prolonged thermal era. Not isolated heat waves, but expanding periods of atmospheric stagnation capable of fundamentally reshaping how entire regions experience summer itself. For most of modern American history, the western United States operated under an assumption so deeply embedded into society that few people ever questioned it. The assumption was simple: the water would always return. Snow would fall in the mountains, rivers would refill reservoirs, and the great engineered systems of the American West would continue functioning as they always had. But tonight, that assumption is beginning to fracture, because across much of the western United States, water reserves are declining faster than many long-term projections originally expected. And the pace of this decline is starting to alarm hydrologists, climate scientists, and resource planners alike. The Colorado River Basin now stands at the center of this unfolding crisis. Stretching across 7 states and supporting approximately 40 million people, the river system functions as one of the most important freshwater lifelines in North America. Yet over the past decades, average river flows have steadily weakened as temperatures increased across the basin. The problem is not simply reduced precipitation. Rising heat itself is extracting more moisture from soil, forests, and waterways through evaporation. Even during years with near normal snowfall, warming temperatures often reduce how efficiently that water survives into summer. More moisture disappears back into the atmosphere before it can stabilize reservoirs downstream. Lake Mead and Lake Powell have become powerful visual symbols of this transformation. Once celebrated as triumphs of 20th century engineering, both reservoirs have repeatedly approached historically low levels in recent years. Vast mineral stains now ring their shorelines, marking where water once stood decades earlier. Hydroelectric generation capacity has periodically come under threat as water elevations decline toward critical thresholds. While wet winters occasionally provide temporary relief, long-term trends continue pointing toward increasing structural stress across the basin. Groundwater systems are also undergoing pressure. As surface water becomes less reliable, agriculture and cities increasingly turn underground. Massive aquifers accumulated over thousands of years are being depleted far faster than they naturally recharge. In some regions of the high plains, groundwater levels have dropped dramatically over the past century due to irrigation demand combined with prolonged drought conditions. And once deep aquifers are exhausted, recovery may require centuries rather than years. Scientists now warn that parts of the American West may be transitioning toward a fundamentally drier baseline climate. This does not mean rain will disappear entirely. Storms will still occur. Floods may even intensify in some regions due to atmospheric warming. But the long-term balance between incoming water and evaporative loss is shifting. The atmosphere is demanding more moisture than landscapes can consistently replace. And this imbalance spreads through every layer of society. Agriculture becomes more vulnerable. Energy systems strain under rising cooling demand. Forests weaken under prolonged drought stress. Wildfire seasons lengthen. Insurance systems destabilize. Migration pressures increase. Entire regional economies begin operating inside conditions they were never originally designed to handle. What makes this especially unsettling is that many current models suggest the most severe consequences may still lie ahead. Because drought is not a single event. It is a compounding process. Each dry year weakens the resilience of the next. Reservoirs lose recovery capacity. Soil moisture baselines decline. Vegetation becomes increasingly stressed. And eventually the entire climate system of a region begins behaving differently than it did historically. The American West still has water. Rivers still flow. Snow still falls. But beneath the surface, the long-term balance sustaining modern life across the region is becoming increasingly fragile. There was a time when wildfire season in the United States followed a relatively predictable rhythm. Fires peaked during late summer, remained largely confined to specific regions, and eventually weakened as autumn rains return. But that rhythm is now beginning to collapse. Across the western United States, scientists and fire behavior specialists are observing the emergence of something far more dangerous than traditional wildfire seasons. Modern megafires are becoming larger, faster, hotter, and more unpredictable than many historical fire models were originally designed to simulate. And the atmosphere itself may now be helping these fires evolve into entirely new forms of environmental disaster. One major reason is fuel accumulation combined with prolonged drought stress. Forests weakened by heat and moisture loss become increasingly vulnerable to insects, disease, and debate. Millions of trees across western North America have already died from combinations of drought stress and bark beetle infestations over recent decades. These dead forests act as enormous reservoirs of dry fuel waiting for ignition. Once fire enters these landscapes under extreme atmospheric conditions, suppression becomes extraordinarily difficult. But the atmosphere above the fire may be the most terrifying part. Under conditions of high heat, low humidity, unstable air, and strong wind shear, large wildfires can begin generating their own weather systems. Massive columns of heated air rise thousands of feet upward, pulling oxygen inward from surrounding regions and intensifying combustion below. In some cases, these smoke plumes from towering pyrocumulus clouds capable of producing lightning, turbulent wind bursts, and even fire tornadoes. Scientists have documented multiple cases where megafires effectively created self-sustaining atmospheric systems that accelerated their own spread. During Australia's catastrophic black summer fires of 2019 and 2020, some pyrocumulonimbus clouds injected smoke directly into the stratosphere, where it circled the planet for months. Similar behavior has increasingly appeared in North America as well. The terrifying implication is that under sufficient atmospheric instability, fires no longer behave merely as ground events. They begin interacting dynamically with the atmosphere itself. This creates conditions where fire behavior becomes increasingly nonlinear and difficult to predict. A small ignition can suddenly transition into explosive growth if atmospheric thresholds align correctly. Wind shifts intensify unexpectedly. Ember storms travel miles ahead of fire fronts. Entire communities may receive evacuation orders with very little warning. Climate researchers increasingly believe warming temperatures are shifting the probability distribution toward more frequent extreme fire behavior. Longer drought periods to high vegetation earlier in the year. Heat domes intensify atmospheric instability. Snowpack melts earlier, extending fire season duration. And vapor pressure deficit progressively removes moisture from landscapes before peak summer even arrives. In some regions, fire season now lasts nearly year-round. California has already experienced devastating fires during months once considered relatively safe. The line between fire season and non-fire season is beginning to disappear. But perhaps the most disturbing aspect of modern megafires is their relationship with climate feedback loops. Fires release enormous amounts of carbon dioxide into the atmosphere, reducing the ability of forests to function as carbon sinks. Smoke particles alter atmospheric chemistry and radiation balance. Burned landscapes absorb more solar heat after vegetation disappears. And repeated fire cycles can permanently transform ecosystems from forests into shrublands or grasslands, incapable of storing previous levels of moisture, carbon. In other words, megafires are no longer simply consequences of climate stress. They are increasingly becoming amplifiers of that stress. The system feeds itself. Heat dries forests. Forests burn. Fires intensify warming. Warming dries forests even further. And somewhere inside that expanding cycle, the American West may already be entering environmental conditions unlike anything modern civilization has previously experienced. Most people experience climate change as weather. The heat wave, the drought, the wildfire, a storm. But the deeper risk emerging beneath all of these events is something far more structural. Because modern civilization does not simply depend on stable weather. It depends on stable food systems. And those systems are far more fragile than they appear. The United States possesses one of the most productive agricultural systems in human history. Vast networks of farms across California, the Midwest, the Great Plains, and the Mississippi River Basin supply enormous portions of global grain, meat, dairy, fruits, and vegetables. But this productivity relies on an extremely delicate balance of water availability, seasonal timing, soil health, transportation infrastructure, fertilizer inputs, and climatic stability. When that balance begins destabilizing, consequences spread rapidly through the economy. Drought already affects agriculture in multiple ways simultaneously. Reduced snowpack lowers irrigation supply. Heat waves stress crops during critical growth periods. Dry soil reduces germination success. Livestock suffer under prolonged thermal stress. Wildfires damage grazing land and disrupt transportation routes. Even short-term heat spikes during pollination periods can significantly reduce crop yields for corn, wheat, and soybeans. Scientists are especially concerned about compound events, situations where multiple climate extremes occur simultaneously. A single drought region can often be managed through imports from unaffected areas. But if heat waves, droughts, or floods strike multiple agricultural regions at once, the global food system becomes far more vulnerable. Recent years have already provided glimpses of this instability. Drought conditions across parts of the United States, combined with heat extremes in Europe and Asia, have periodically strained grain markets and intensified food price volatility worldwide. The modern food system operates with remarkable efficiency, but that efficiency often leaves little redundancy. Supermarkets appear full because supply chains function continuously unprecisely. Yet beneath the surface, many systems operate close to optimization limits. Disruptions in transportation, fertilizer production, water access, or crop timing can rapidly ripple through global markets. California alone produces enormous percentages of America's fruits, vegetables, and nuts. But much of this production depends heavily on irrigation systems, increasingly strained by declining water reserves. Meanwhile, parts of the Midwest face rising flood risks alongside intensifying summer heat, creating a dangerous combination of planting instability and crop stress. Soil moisture loss itself creates additional problems. Healthy soil acts like a sponge, storing water, stabilizing ecosystems, and protecting crops during dry periods. But prolonged drought gradually degrades soil structure, reducing resilience against future extremes. Once topsoil becomes damaged, recovery may require years or decades. Some researchers worry parts of the Great Plains could face increasing desertification, risk under prolonged warming and water depletion trends. And unlike technological systems, ecosystems do not always recover smoothly once thresholds are crossed. Pollinator populations decline under environmental stress. Forest loss alters rainfall patterns. Groundwater depletion weakens long-term agricultural viability. Heat stress changes livestock productivity. Every layer interacts with every other layer. This is why many climate scientists increasingly frame food security as one of the central challenges of the 21st century. Not because civilization will suddenly run out of food overnight, but because the stability and predictability underlying modern agricultural abundance may gradually erode under mounting environmental pressure. The terrifying reality is that modern societies are deeply interconnected. A drought in one region can affect prices globally. A failed harvest can destabilize economies thousands of miles away. And if prolonged atmospheric instability continues expanding across major agricultural zones, the consequences may extend far beyond weather itself. Because civilizations are often more resilient to single disasters than they are to sustained uncertainty. One of the least visible consequences of escalating drought and heat is happening inside the electrical systems modern civilization depends upon every every day. Because the power grid of the United States was designed for a climate that no longer fully exists. And as temperatures continue rising across large sections of North America, the grid itself is beginning to operate under levels of stress it was never originally engineered to handle. Extreme heat increases electricity demand almost immediately. Air conditioners run longer. Refrigeration systems work harder. Water infrastructure consumes more energy. Entire cities begin drawing enormous amounts of electricity simultaneously. During major heat waves, power demand can surge toward critical thresholds within hours. But the dangerous part is that heat also weakens the grid's ability to function at the exact same time demand rises. Transmission lines lose efficiency as temperatures increase. Infrastructure overheats. Transformers experience higher failure risk. Hydroelectric production declines as reservoirs fall. Thermal power plants struggle when cooling water becomes too warm. The entire system begins straining from both sides simultaneously. Recent summers have already exposed this vulnerability repeatedly. California experienced rolling blackout warnings during prolonged heat waves as electrical demand approached dangerous levels. Parts of Texas faced severe grid instability during major weather extremes. Across the Southwest, utilities increasingly warn that future summers may place enormous pressure on regional energy systems. And as heat domes become more persistent, the problem compounds. The terrifying reality is that modern cities cannot function for long without reliable electricity. Water distribution, hospitals, transportation systems, internet infrastructure, food refrigeration, fuel pumps, communication networks, and emergency services all depend on continuous power. During extreme heat events, prolonged outages become especially dangerous because nighttime temperatures often remain elevated inside urban heat islands. Buildings trap warmth. Asphalt radiates stored heat back into the atmosphere. Human bodies lose recovery time. Heat stress accumulates day after day. Scientists increasingly warn that compound disasters may become more common in the decades ahead. A drought intensifies heat. Heat strains the grid. Grid failures reduce cooling access. Wildfires damage transmission lines. Smoke reduces solar generation. Water shortages weaken hydroelectric output. Multiple systems begin failing together instead of separately. And once cascading failures begin, recovery becomes far more difficult than most people realize. The American grid still functions. Cities remain illuminated. Air conditioners still hum through the night. But beneath the surface, the infrastructure sustaining modern life is increasingly operating inside environmental conditions it was never designed to survive indefinitely. One of the most unsettling ideas in climate science is that the atmosphere does not simply react to events, it stores them. Every wildfire, every drought, every heat wave, and every warming ocean leaves behind traces that influence the future behavior of the system itself. In a sense, the atmosphere remembers. When forests burn, massive amounts of carbon dioxide enter the air, trapping additional heat. When Arctic ice melts, darker ocean water absorbs more solar radiation, accelerating warming further. When drought dries soil, less moisture evaporates into the atmosphere, allowing temperatures to rise even faster during future heat events. Each event subtly alters the baseline conditions beneath the next. This is why climate scientists often speak about feedback loops. A feedback loop occurs when the consequences of warming begin amplifying the original warming itself. Some feedbacks remain relatively weak. Others may become extremely powerful if certain thresholds are crossed. And across North America, researchers are increasingly worried that multiple feedback systems may now be interacting simultaneously. Drought intensifies wildfire risk. Wildfires release more carbon. Carbon traps more heat. Heat increases atmospheric thirst. Atmospheric thirst dries landscapes even faster. The cycle reinforces itself. The terrifying part is that these systems often accelerate gradually at first before suddenly becoming much more visible. For years, changes appear manageable. Then thresholds emerge. Reservoirs decline faster than expected. Fire seasons expand beyond historical boundaries. Heat waves last longer. insurance systems destabilize. Entire ecosystems struggle to recover between extremes. And because the atmosphere operates as one interconnected system, changes in one region often influence conditions far away. Warming oceans reshape jet streams. Shrinking snowpack alters river systems. Arctic amplification affects atmospheric circulation across the northern hemisphere. Smoke from megafires travels across continents. The climate system is not fragmented. It is deeply connected. Modern civilization developed during one of the most climatically stable periods in human history. Agriculture, infrastructure, cities, and economies all evolved around relatively predictable environmental patterns. But scientists increasingly believe that stability itself may now be weakening, not collapsing overnight, but slowly becoming more erratic, more persistent in its extremes, and less tied to the historical boundaries societies once depended upon. The atmosphere remembers every imbalance added into the system. And tonight, those accumulated imbalances may finally be starting to reshape the future in ways humanity is only beginning to understand. Far from the deserts of Arizona and the dry reservoirs of the American West, another transformation is unfolding across the oceans themselves. And although most people rarely think about it, the oceans control an enormous portion of Earth's climate system. They store heat, redistribute energy across the planet, shape atmospheric circulation, and influence rainfall patterns of miles away, which means what happens in the Pacific Ocean does not stay in the Pacific Ocean. It eventually reaches North America. One of the most important climate patterns affecting the United States is the El Niño, Southern Oscillation, a shifting cycle of ocean temperatures and atmospheric pressure across the tropical Pacific. During El Niño phases, warmer Pacific waters alter global weather patterns, often bringing wetter conditions to parts of the southern United States. During La Niña phases, cooler Pacific waters can intensify drought across the southwest and western plains. But scientists now believe long-term warming may be amplifying the volatility of these natural cycles themselves. Ocean temperatures worldwide are reaching extraordinary levels. Large sections of the Atlantic and Pacific have recently recorded marine heat anomalies far above historical averages. Warmer oceans release additional heat and moisture into the atmosphere, injecting more energy into weather systems across the globe. Hurricanes intensify faster. Atmospheric rivers carry more moisture. Heat domes become more persistent. And the jet stream itself may become increasingly unstable under these changing thermal gradients. The terrifying reality is that the atmosphere above North America is partially being driven by oceans that are now warmer than modern civilization has ever experienced. Some researchers worry that this additional oceanic energy may increase the likelihood of compound climate extremes, situations where drought, heat, storms, and wildfire risk overlap simultaneously. And because oceans respond slowly, many of the warming patterns already measured today may continue influencing the atmosphere for decades, even if emissions eventually stabilize. The seas appear calm from the shoreline. But beneath the surface, the engines shaping continental climate are already changing. Drought is usually imagined as something temporary. A bad season. A difficult year. Eventually the rains return and the system recovers. But a megadrought is something entirely different. A megadrought is not simply a lack of rainfall. It is a prolonged climate event capable of lasting decades and reshaping entire civilizations. And according to a growing number of climate studies, parts of the western United States may already be experiencing the early stages of one. Scientists use tree rings, lake sediments, and ancient climate records to reconstruct drought patterns extending back more than 1,000 years. These paleomystical records reveal that North America has experienced massive long-duration droughts before, some lasting 20 to 30 years or long durations or longer. Entire indigenous societies adapted to these shifts centuries before modern infrastructure existed. Rivers changed behavior. Agricultural systems collapsed. Human migration patterns transformed across the continent. What alarms scientists today is that modern warming may now be intensifying natural drought cycles beyond historical norms. Research published over the last decade suggests the current southwestern drought may already rival some of the most severe megadroughts seen in at least 1,200 years. Rising temperatures amplify evaporation, dry soil faster, weaken snowpack, and intensify atmospheric thirst across already vulnerable landscapes. This means modern drought is being driven not only by reduced precipitation, but also by warming itself. The atmosphere extracts more moisture from the land than historical systems evolved to tolerate. And unlike ancient societies, modern civilization depends on enormous fixed infrastructure systems that require stable water supplies. Massive cities, industrial agriculture, hydroelectric networks, interstate water agreements, and millions of acres of irrigation all assume a climate stability that may no longer fully exist. The terrifying part is that megadroughts do not announce themselves dramatically at first. They emerge slowly. Reservoirs gradually decline. Soil moisture weakens year after year. Forests become stressed. Fire seasons lengthen. Water restrictions expand incrementally. Then eventually, entire regions realize the baseline itself has changed. Scientists still debate exactly how severe future drought conditions may become across North America. But many increasingly agree on one disturbing point. The American West may now be entering a climate regime more arid than the one modern society was originally built upon. And if that transition continues accelerating, the consequences may extend far beyond weather alone. For many Americans, the Dust Bowl feels like ancient history, a black and white disaster buried somewhere in textbooks and documentaries. But climate scientists increasingly view it as something else entirely, a warning. During the 1930 seconds, massive drought combined with cruel and management transformed huge sections of the Great Plains into collapsing dust fields. Crops failed across millions of acres. Entire communities were displaced. Dust storms darkened skies so severely that some cities required lights during daytime hours. Economic collapse spread across farming regions already weakened by the Great Depression. But what makes the Dust Bowl especially important today is not simply what happened. It is how vulnerable the continent proved once climate stress crossed critical thresholds. The American landscape at that time still contained far fewer people, less infrastructure, and dramatically lower water demand than exists today. Yet even under those conditions, prolonged drought reshaped the country socially, economically, and politically. Modern America is far more technologically advanced, but also far more dependent on stable climate systems. Agriculture now operates at enormous industrial scales. Water systems support tens of millions of people in naturally arid regions. Electrical infrastructure, transportation networks, and food supply chains are deeply interconnected, which means prolonged climate instability today may create vulnerabilities very different from those of the 1930 seconds, but potentially just as serious. The terrifying reality is that some modern drought indicators are beginning to approach Dust Bowl era intensity in certain regions. But unlike the 1930 seconds, today's warming atmosphere is simultaneously increasing evaporation and atmospheric thirst. Scientists worry this combination could produce future drought conditions that exceed historical expectations in both duration and severity. The Dust Bowl was not caused by climate change alone. It emerged from the interaction between environmental stress and human systems unprepared for it. And that may be exactly why scientists continue studying it so carefully today. Because history suggests civilizations often appear stable until environmental conditions quietly move beyond the boundaries those civilizations were built to survive. Most people imagine climate migration as something dramatic and obvious. Entire cities flooding. Millions fleeing disasters overnight. But, in reality, migration often begins quietly. Families relocate after repeated wildfires. Farmers leave regions where water has become unreliable. Insurance costs rise beyond affordability. Heat becomes unbearable for older populations. Economic pressure slowly pushes people elsewhere long before headlines notice the pattern. And across parts of the United States, this invisible migration may already be underway. In some western regions, rising wildfire risk and escalating insurance losses are beginning to reshape housing markets. Certain insurers have reduced coverage or withdrawn entirely from extremely fire-prone areas. Meanwhile, prolonged drought threatens agricultural stability across portions of the southwestern Great Plains. Water shortages place additional pressure on communities already operating near environmental limits. Climate researchers increasingly believe population movement may become one of the defining social consequences of long-term environmental instability during the 21st century. Not because entire regions suddenly become uninhabitable overnight, but because maintaining normal life gradually becomes more expensive, uncertain, and difficult. Heat increases energy costs. Water restrictions affect agriculture and industry. Repeated disasters strain local economies. Infrastructure repairs become constant. Over time, people adapt by moving. Historically, civilizations have always migrated in response to environmental stress. Ancient droughts altered settlement patterns across continents. Water scarcity influenced the rise and decline of empires. Even modern urbanization has often followed access to stable resources. The difference today is scale. Modern infrastructure ties enormous populations to regions increasingly exposed to heat, drought, flooding, and wildfire risk simultaneously. The American Southwest remains one of the fastest-growing regions in the country despite mounting climate stress. Cities like Phoenix and Las Vegas continue expanding in landscapes naturally defined by limited water availability. For now, technological systems still support this growth. Reservoirs, groundwater extraction, and massive engineering projects continue sustaining urban life. But scientists increasingly question how resilient some of these systems remain under prolonged warming scenarios extending decades into the future. The terrifying part is that climate migration does not only affect the people leaving, it reshapes the regions receiving them as well. Housing markets shift. Infrastructure strains increase. Water demand rises elsewhere. Economic pressure spreads outward across states and industries. Migration becomes not simply a humanitarian issue, but a structural transformation of society itself. And because these changes happen gradually, societies often fail to recognize them until the patterns are already deeply established. The atmosphere changes first, then ecosystems, then economics, and eventually human geography follows. To most people, forests appear permanent, ancient, stable. But forests are living systems constantly balancing moisture, temperature, sunlight, and biological survival. And across large sections of North America, the balance is beginning to fail. Scientists studying western forests have documented growing signs of widespread ecological stress linked directly to prolonged drought and rising temperatures. Trees weakened by heat lose their ability to transport water efficiently from roots to leaves. Photosynthesis slows. Growth declines. Some species begin shutting down critical biological processes simply to survive prolonged dry periods. Others die outright after years of cumulative stress. And once forests weaken, they become vulnerable to secondary threats that can spread with astonishing speed. One of the most destructive has been the bark beetle. Warmer winters allow beetle populations to survive in greater numbers, while drought-stressed trees lose part of their natural defense system against infestation. Over recent decades, millions of acres of forest across the western United States and Canada have suffered large-scale die-offs linked to this combination of heat, drought, and insect expansion. Entire mountainsides once covered in green pine now stand brown and skeletal. The terrifying part is that dead forests fundamentally alter the behavior of fire itself. Dry standing timber creates enormous fuel reservoirs capable of burning with extraordinary intensity once ignition occurs. Fires move faster, burn hotter, generate larger smoke plumes, and after severe burns, forests may struggle to regenerate under hotter and drier conditions. In some areas, ecosystems that historically recovered after wildfire are beginning to transition towards shrublands or grasslands instead. Scientists increasingly warn that certain forests may eventually cross ecological tipping points where recovery toward previous conditions becomes extremely difficult. The forests still stand for now, but biologically, many are already operating under levels of stress unseen in modern history. One of the most dangerous changes happening across the United States is something many people barely notice consciously at first. The nights are getting warmer. Historically, even during major summer heatwaves, nighttime cooling provided critical recovery time for ecosystems, infrastructure, and human bodies. Temperatures would fall after sunset, allowing cities, soil, forests, and people to release accumulated heat. But modern warming is increasingly disrupting that recovery cycle. Across many parts of the country, nighttime temperatures are rising faster than daytime temperatures themselves. This creates a particularly dangerous form of prolonged heat stress because the body never fully cools down between hot days. Sleep becomes disrupted. Cardiovascular strain increases. Vulnerable populations face greater health risks. And urban areas become especially dangerous due to the urban heat island effect. Concrete, asphalt, and buildings absorb solar energy throughout the day and slowly release it overnight, trapping warmth inside cities long after sunset. During severe heat waves, some urban neighborhoods now remain dangerously warm even at midnight. Scientists are increasingly concerned because ecosystems also depend on nighttime recovery. Plants regulate water loss partly through cooler nighttime respiration. Soil moisture stabilizes more effectively under lower temperatures. Wildlife behavior evolved around predictable cooling cycles. When nights remain unusually warm for extended periods, biological stress accumulates across entire landscapes. The terrifying reality is that heat becomes far more dangerous when recovery disappears. A single hot afternoon is survivable for most systems. Weeks of relentless heat without nighttime relief become something else entirely. And as heat domes grow more persistent across North America, researchers fear this loss of nighttime cooling may become one of the defining environmental signatures of the coming decades. When most people think about drought and wildfire, they imagine flames, heat, and dry landscapes. But one of the largest consequences often travels silently through the atmosphere itself. Smoke. In recent years, wildfire smoke has evolved from a regional problem into a continental-scale atmospheric event. Massive smoke plumes from western North American fires have repeatedly spread thousands of miles across the United States, darkening skies over cities far removed from the original flames. In some cases, smoke from Canadian wildfires has reached Europe. The atmosphere is carrying these fires across entire hemispheres. Wildfire smoke contains an extremely dangerous mixture of microscopic particles, carbon compounds, ozone precursors, and toxic chemicals produced by burning vegetation and human infrastructure. The smallest particles, known as PM2.5, are especially harmful because they penetrate deep into the lungs and bloodstream. Scientists have linked prolonged smoke exposure to respiratory illness, cardiovascular stress, neurological impact, and increased mortality risk during severe events. The terrifying part is that smoke can affect populations far beyond fire zones themselves. Millions of people may experience unhealthy air quality, even while living hundreds or thousands of miles away from active fires. During major smoke outbreaks, entire skylines turn orange. Sunlight dimmed. Air quality indexes surge into hazardous territory. Schools close. Hospitals see rising respiratory cases. And because megafires are becoming larger and longer lasting, smoke seasons are now expanding alongside fire seasons themselves. Researchers increasingly worry that smoke exposure may become one of the most widespread health consequences of climate-driven wildfire escalation in North America. The fires do not need to reach your city physically. The atmosphere brings part of them to you anyway. Modern civilization depends heavily on a hidden assumption that disasters remain statistically manageable. Insurance systems function by calculating risk based on historical probabilities. Floods, Fires, storms, and heat waves are expected to occur occasionally, but not constantly and not everywhere at once. But climate instability is beginning to challenge that assumption. Across parts of the United States, insurance companies are already struggling to manage escalating disaster losses linked to wildfire, hurricanes, flooding, and severe storms. In some high-risk wildfire regions, insurers have reduced coverage, raised premiums dramatically, or stopped issuing new policies entirely. California has become one of the clearest examples of this growing tension. As megafires intensified over recent years, insured losses climbed into tens of billions of dollars. Entire communities became financially difficult to insure under traditional models. The problem is not simply the size of individual fires. It is the increasing unpredictability and frequency of extreme events themselves. Historical risk models were built around past climate behavior. But if climate conditions are shifting outside historical ranges, those models become harder to trust. The terrifying reality is that insurance functions as one of the foundational stabilizers of modern economies. Mortgages, infrastructure investment, housing markets, business expansion, and disaster recovery all rely on the assumption that risk can be distributed predictably across society. But when environmental instability accelerates faster than financial systems can adapt, cracks begin spreading outward. Premiums rise. Housing affordability weakens. Rebuilding becomes harder. Entire regions face increasing economic pressure after repeated disasters. Scientists and economists increasingly warn that climate change is not only an environmental issue, it is becoming a systemic financial issue as well. Because once risks become difficult to price, modern economic systems themselves begin operating under growing uncertainty. And uncertainty, over long enough periods, changes how civilizations function. Most people think drought only affects what they can see above the ground. Dry rivers, dead grass, shrinking reservoirs. But one of the most important changes is happening underneath our feet. The soil itself is beginning to change. Healthy soil is not simply dirt. It is a living system filled with microorganisms, fungi, organic matter, moisture pathways, and delicate biological relationships that support entire ecosystems above it. When soil remains healthy, it stores water efficiently, stabilizes plant growth, reduces erosion, and even helps regulate atmospheric carbon. But prolonged drought slowly weakens these systems. As moisture disappears, microbial activity declines. Organic matter breaks down differently. Soil structure becomes less stable. Cracks form. Wind erosion intensifies. Water that does arrive during storms often runs off more quickly instead of soaking downward. This creates a dangerous feedback loop. Dry soil absorbs less moisture. Less moisture means hotter land surfaces. Hotter surfaces intensify evaporation and atmospheric heating. The drought deepens further. Scientists have already observed parts of the American Western Great Plains moving toward this kind of long-term soil degradation. And once large landscapes begin losing biological resilience, recovery becomes far slower than many people realize. A single wet season cannot instantly rebuild damaged ecosystems. Some soil systems require decades to fully recover after prolonged environmental stress. The terrifying part is that civilizations depend on stable soil more than almost anything else. Agriculture, water cycles, ecosystems, forests, and food systems all begin with the ground itself. And if the soil weakens long enough, the consequences spread upward through every layer of society above it. Extreme heat does not only stress infrastructure and ecosystems, it affects human cognition itself. Scientists studying prolonged heat exposure have found increasing evidence that high temperatures influence concentration, decision-making, emotional regulation, sleep quality, and even aggression levels. The human brain operates within narrow thermal boundaries. When body temperature rises excessively, cognitive efficiency begins declining. Memory weakens. Reaction times slow. Fatigue increases. And under prolonged heat stress, mental performance may deteriorate significantly, even in otherwise healthy individuals. Sleep disruption becomes especially dangerous because nighttime heat prevents proper physiological recovery. People become chronically exhausted during extended heat waves. Researchers have linked prolonged heat exposure to rising emergency room visits, increased workplace accidents, and worsening mental health outcomes. Some studies even suggest extreme heat correlates with increases in violence and social instability during severe events. Cities are particularly vulnerable because urban heat islands trap warmth long after sunset. Concrete and asphalt continue radiating stored energy throughout the night, creating environments where millions of people experience continuous thermal stress without meaningful cooling periods. Vulnerable populations face the highest risks: older adults, outdoor workers, low-income communities, and individuals without reliable air conditioning. The terrifying reality is that human civilization evolved within relatively stable climatic ranges. Modern societies often assume technological systems can fully protect populations from environmental extremes, but sustained heat challenges those assumptions in subtle ways. Productivity declines, health systems strain, psychological stress accumulates. And when heat combines with drought, smoke, blackouts, and economic pressure simultaneously, societies may begin experiencing forms of chronic stress modern systems were never fully designed to manage. The atmosphere is not only reshaping landscapes, it may gradually be reshaping human behavior itself. One of the deepest misconceptions about climate change is the belief that warming simply means more heat. In reality, warming alters the entire planetary water cycle. And across North America, scientists are increasingly observing signs that this balance is beginning to destabilize. A warmer atmosphere can hold significantly more water vapor than a cooler one. This means evaporation intensifies across oceans, lakes, rivers, forests, and soil. But instead of producing evenly distributed rainfall, the atmosphere often releases this moisture in increasingly extreme bursts. Long dry periods become interrupted by intense storms, flash floods, or atmospheric rivers capable of delivering enormous rainfall within short periods of time. The result is a climate system swinging between extremes. Droughts become deeper. Rain events become more violent. Snowpack becomes less reliable. Water arrives at the wrong time in the wrong place, and often too quickly for ecosystems or infrastructure to absorb efficiently. Scientists sometimes describe this as the acceleration of the hydrological cycle itself. The entire water system is moving faster and more chaotically than before. California provides one of the clearest examples. Years of severe drought have repeatedly been interrupted by powerful atmospheric river events capable of causing catastrophic flooding and landslides. Reservoirs may rise temporarily, yet long-term water stability still weakens because the underlying climate system remains increasingly erratic. The terrifying reality is that modern civilization depends not only on water quantity, but on water timing and predictability. Agriculture, reservoirs, hydroelectric systems, and entire cities were built around historical seasonal patterns. But those patterns are becoming less stable. The atmosphere still moves water across the continent, but increasingly, it no longer behaves according to the rhythm societies evolved around. Nature often appears resilient because ecosystems can survive enormous stress for long periods before suddenly changing very quickly. Forests regrow after fires. Rivers recover after droughts. Grasslands return after storms. But scientists increasingly warn that some ecosystems across North America may now be approaching tipping points beyond which recovery becomes uncertain. A tipping point occurs when gradual environmental stress pushes a system into a fundamentally different state. In forests, repeated drought and megafire cycles may prevent tree regeneration before the next fire arrives. In drylands, vegetation loss can expose soil to erosion and desertification. Wetlands weakened by heat and water loss may collapse into entirely different ecological structures. The terrifying part is that ecosystems often appear stable until thresholds are crossed. Then change accelerates rapidly. Scientists studying western forests have already observed areas where post-fire recovery is failing under hotter and drier conditions. Seedlings struggle to survive. Soil moisture disappears too quickly. Grass and shrubs replace former tree cover. Once enough ecological transitions occur, local climate conditions may begin changing as well. Forests regulate temperature, humidity, rainfall patterns, and carbon storage. When they disappear, the atmosphere above them changes too. This creates another feedback loop. Ecosystem loss intensifies climate stress, which weakens ecosystems even further. Some researchers now believe parts of the American West could experience long-term biome shifts over the coming century if warming and drought continue accelerating. Forests that existed for thousands of years may gradually transition into more arid landscapes, fundamentally different from those modern societies inherited. The ecosystems still exist tonight. Trees still stand. Rivers still flow. But beneath the surface, some natural systems may already be approaching limits they cannot easily reverse once crossed. Far north above the United States, another transformation is unfolding at extraordinary speed. The Arctic is warming nearly 4 times faster than the global average, and scientists increasingly believe this rapid warming may be influencing weather patterns across the entire northern hemisphere. For most of human history, the Arctic functioned like a planetary cooling system. Vast areas of sea ice reflected enormous amounts of solar radiation back into space, helping regulate Earth's temperature balance. But as temperatures rise, that ice is shrinking dramatically. Dark ocean water replaces reflective ice surfaces, absorbing more heat and accelerating warming further. This process is known as Arctic amplification, and it may be one of the most important climate feedback loops currently active on Earth. The terrifying part is that Arctic warming does not stay confined to the Arctic. Some atmospheric researchers believe it may weaken the temperature gradient between the equator and the poles, contributing to slower and more unstable jet stream behavior. When the jet stream weakens, other systems can store more easily over continents. Heat domes linger longer. Cold outbreaks plunge farther south. Droughts persist. Flooding events intensify. The atmosphere becomes less stable overall. Scientists continue debating exactly how large this influence may be, but many agree the Arctic is no longer behaving like the stable frozen system modern civilization inherited. The North is changing rapidly. And because the atmosphere connects the entire hemisphere together, those changes may increasingly shape the future climate of North America itself. One of the strangest aspects of environmental change is how easily humans adapt psychologically to worsening conditions. A record heatwave feels shocking at first. Then, another arrives the following year. Wildfire smoke darkens skies once considered safe. Reservoirs decline further. Insurance costs rise. And slowly, what once felt extraordinary begins feeling normal. Scientists sometimes refer to this as shifting baselines. Each generation unconsciously accepts the environmental conditions it grows up with as standard, even if those conditions would have seemed alarming decades earlier. This psychological adaptation makes long-term climate change uniquely difficult to perceive emotionally. Civilization adjusts gradually while the system underneath continues changing. The terrifying reality is that some climate transformations may already be unfolding faster than public perception itself. Fire seasons expand. Heat records fall repeatedly. Ecosystems weaken. Yet daily life often continues just normally enough for societies to postpone confronting the scale of the transition. Humans are remarkably adaptable creatures. That adaptability has helped civilization survive countless challenges throughout history. But it can also create dangerous complacency when slow-moving risks accelerate beneath the surface. Scientists increasingly warn that climate instability is not simply a future problem waiting decades ahead. Many of its structural changes are already measurable right now, across water systems, agriculture, atmospheric circulation, forests, and oceans. The atmosphere is shifting gradually enough for people to normalize it, but quickly enough for ecosystems to struggle keeping pace. And perhaps the most unsettling possibility is this: the future may not arrive all at once. It may arrive slowly, quietly, almost invisibly, until one day entire societies realize the stable world they once assumed would always exist has already begun slipping away. Most drought discussions focus on rainfall, rivers, or reservoirs. But beneath the Great Plains lies another system modern America depends upon almost invisibly: groundwater. Hidden underground across parts of Texas, Oklahoma, Kansas, Nebraska, and several surrounding states sits the Ogallala Aquifer, one of the largest freshwater reserves on Earth. For decades, this underground water system helped transform the central United States into one of the most productive agricultural regions in human history. Millions of acres of farmland depended on it. Entire economies grew around it. But tonight, scientists warn that parts of this aquifer are declining far faster than natural recharge can replace. In some regions, groundwater accumulated over thousands of years is being depleted within generations. And unlike reservoirs, underground depletion remains mostly invisible until wells begin failing. The terrifying reality is that groundwater loss compounds drought itself. As surface water becomes unreliable, agriculture pumps more heavily underground. But once groundwater drops too low, recovery may require centuries. Some areas may never fully recharge under modern climate conditions. The plains still produce crops. Irrigation systems still run. But underneath the surface, one of America's hidden lifelines is slowly shrinking. For most of history, wildfire smoke remained relatively close to Earth's surface. But modern megafires are becoming so powerful that some now inject smoke directly into the upper atmosphere itself. Scientists studying recent fires in North America and Australia observed pyrocumulonimbus clouds carrying smoke particles into the stratosphere, a region of the atmosphere where material can remain suspended for months. This changes the scale of wildfire entirely. Fires no longer affect only local ecosystem. They begin influencing atmospheric chemistry and global climate systems themselves. Smoke particles in the stratosphere can alter radiation balance, scatter sunlight, and interact with cloud formation processes across enormous distances. Some researchers are now investigating whether large smoke injections may even slightly reinforce the atmospheric blocking patterns that helped sustain the fires initially. The science remains ongoing, but the possibility itself is deeply unsettling. The atmosphere may be entering feedback loops where megafires partially intensify the environmental conditions supporting future megafires. Heat dries forests. Forests burn. Smoke alters atmospheric behavior. Drought deepens further. The cycle strengthens itself. The fires still appear local from the ground. But from the perspective of the atmosphere, they are increasingly planetary events. Modern cities often create the illusion that technology has fully conquered geography. Las Vegas glows in the desert. Phoenix continues expanding beneath extreme heat. Massive suburbs stretch across landscapes that historically supported very small populations. But climate scientists increasingly warn that parts of the American Southwest may now be approaching environmental limits modern infrastructure alone cannot endlessly overcome. Much of the region naturally exists within arid or semi-arid climate zones. Historically, water availability constrained settlement growth for centuries. But 20th century engineering changed that equation temporarily. Reservoirs, aqueducts, groundwater pumping, and interstate river systems allowed massive urban expansion across landscapes previously incapable of supporting millions of people. The terrifying reality is that many of these systems were built during unusually stable and wetter climate periods. Today, that stability is weakening. Rising temperatures intensify evaporation. Snowpack declines. Reservoirs fluctuate more violently. Energy demand surges during prolonged heatwave. Meanwhile, populations continue growing in some of the hottest and driest parts of the continent. Scientists are not suggesting these cities will suddenly disappear, but maintaining them may become increasingly expensive, energy-intensive, and environmentally difficult over the coming decades. Water systems will require constant adaptation. Cooling demand will rise. Infrastructure stress will intensify. And every additional degree of warming increases pressure on systems already operating close to environmental limits. The Southwest still functions tonight. Highways remain crowded. Air conditioning hums across the desert. But underneath the surface, the long-term balance sustaining these cities is becoming increasingly fragile. One of the most unsettling conclusions emerging from modern climate science is not simply that the planet is changing. It is that some parts of the climate system may now be changing faster than human institutions can comfortably adapt. Ecosystems can shift within years. Atmospheric patterns can destabilize within decades. But infrastructure, politics, economics, and urban planning often move far more slowly. Reservoir systems may take generations to redesign. Power grids require enormous investment and time to modernize. Agricultural systems cannot instantly relocate. Insurance markets struggle to price rapidly evolving risks. Governments frequently react after disasters rather than before them. This creates a dangerous mismatch between environmental acceleration and institutional response. Scientists increasingly warn that the challenge of climate instability may not come from any single catastrophe alone. It may come from the cumulative pressure of many overlapping stresses arriving faster than systems were designed to absorb. Heatwaves, droughts, fires, floods, infrastructure strain, food instability, insurance disruption, migration pressure, energy demand. None individually collapse civilization, but together over time, they can gradually erode resilience across multiple layers simultaneously. The terrifying part is that human societies often recognize structural change only after the old system has already begun weakening. And tonight, climate researchers across the world are quietly measuring signs that some of those structural shifts may already be underway. The atmosphere is moving. The oceans are warming. The forests are drying. The water systems are straining. And civilization itself is now racing to adapt inside a climate future arriving faster than many institutions ever expected. Temperature alone does not determine how dangerous heat becomes for the human body. Humidity matters too. And as the atmosphere warms, some regions are beginning to experience combinations of heat and humidity that push human survivability closer to dangerous physiological limits. Scientists measure this using something called wet bulb temperature, a metric combining heat and moisture to estimate how efficiently the body can cool itself through sweat evaporation. Under extremely high wet bulb conditions, sweating stops working effectively. The body begins accumulating heat faster than it can release it. Prolonged exposure can become lethal even for healthy individuals resting in the shade. Historically, such conditions were rare and short-lived. But climate researchers increasingly warn that warming oceans and atmospheric moisture may allow dangerous wet bulb events to become more frequent in parts of the world during the coming decades. The southeastern United States and Gulf Coast are especially vulnerable because high humidity combines with rising temperatures to intensify heat stress dramatically. The terrifying reality is that humans evolved within relatively narrow climatic boundaries. Modern air conditioning helps societies tolerate environments that would otherwise be difficult to inhabit at large scale. But during prolonged heatwaves combined with power failures, infrastructure stress, or economic inequality, vulnerability rises quickly. The atmosphere is not only getting hotter. In some regions, it is becoming biologically harder for the human body itself to endure. At first glance, wildfire and weather appear separate. Weather influences fire, but fire itself seems passive. Yet modern megafires are becoming so massive that they increasingly influence atmospheric conditions around them in return. Large fires generate enormous heat columns capable of altering local wind circulation. Rising smoke plumes create pressure differences that pull additional oxygen inward, intensifying flames further. In extreme cases, fires develop rotating vortices known as fire whirls, essentially tornado-like structures generated by combustion and atmospheric instability. Scientists studying megafires have documented situations where fires create their own storm clouds, produce lightning, and even trigger new ignitions ahead of the main front. This transforms wildfire from a surface event into an atmospheric system interacting dynamically with the environment around it. The terrifying part is that climate warming increases the likelihood of exactly these extreme fire behaviors. Longer droughts dry fuel earlier. Heat domes to stabilize the atmosphere. Wind events spread embers farther. And once fires become large enough, they begin partially shaping their own weather conditions. Some researchers now believe future megafires may increasingly behave unlike anything historical firefighting systems were originally designed to confront. Fires once considered extreme may gradually become part of the new operational baseline. The flames still begin with sparks. But under the atmosphere now forming across parts of North America, those sparks may increasingly evolve into something much larger than civilization expects. When most people imagine drought, they picture empty lakes, cracked soil, and dying vegetation. But drought also changes the atmosphere directly above major cities. As landscapes lose moisture, less water evaporates into the air. This reduces natural cooling and allows urban regions to heat faster and more aggressively during summer months. Scientists call this soil and atmosphere feedback. Dry soil heats the air more efficiently than moist soil because less incoming solar energy is used for evaporation. Instead, more energy converts directly into surface heat. Cities surrounded by drought-stricken landscapes become trapped inside increasingly hostile thermal environments. Asphalt, concrete, and steel absorb heat all day and slowly release it at night, creating massive urban heat islands capable of remaining dangerously warm long after sunset. The terrifying reality is that some American cities are already experiencing nighttime temperatures that would have been considered highly unusual only decades ago. And because the atmosphere above these cities now begins each morning warmer than before, every new heatwave builds on top of accumulated stress from the previous one. The land dries. City heat. The atmosphere traps more warmth. And the cycle continues tightening around millions of people simultaneously. For generations, wildfire season had boundaries. There was a beginning, a peak, and eventually an end. Cooler temperatures and rainfall arrived, allowing landscapes to recover before the next cycle began. But today, scientists increasingly warn that parts of North America may be entering something fundamentally different, a permanent fire era. In California alone, destructive fires have now occurred during months once considered relatively safe. Fire behavior specialists increasingly describe wildfire not as a seasonal threat, but as a year-round environmental condition. Drought, heat, low humidity, and extreme wind events are overlapping more frequently throughout the calendar itself. Snowpack melts earlier. Vegetation cures faster. Atmospheric instability arrives sooner and spring lingers deeper into autumn. The terrifying part is that modern megafires are not simply increasing in frequency. They are also expanding in complexity. Fires interact with drought, smoke, infrastructure, migration, insurance systems, and public health simultaneously. Entire regions may spend months breathing hazardous air while living under evacuation risk and water stress at the same time. Scientists still debate how severe future fire seasons may become. But many increasingly agree on one point: the environmental conditions that historically limited wildfire behavior are weakening. The atmosphere above the western United States is becoming hotter, drier, and more unstable. And if those trends continue long enough, future generations may inherit a continent where large-scale fire is no longer treated as an exception, but as part of normal life itself. For thousands of years, Earth's climate operated within relatively stable boundaries. Storm systems followed recognizable seasonal patterns. Snowpack accumulated within predictable ranges. Rivers rose and fell according to rhythms ecosystems had adapted to over centuries. Human civilization developed inside that stability. Agriculture depended on it. Cities depended on it. Entire economies quietly assumed those patterns would continue. But tonight, climate scientists increasingly believe the atmosphere may be drifting outside parts of its historical memory. Events once considered statistically rare are appearing more frequently. Heat records fall repeatedly. Fire seasons expand beyond previous limits. Rainfall swings between extremes. Atmospheric blocking patterns persist longer than older models expected. The terrifying part is not simply the intensity of individual events. It is the growing sense that the baseline itself may be changing. Historical averages become less reliable. The past becomes a weaker guide for the future. And when societies lose the ability to predict environmental behavior confidently, uncertainty spreads through every layer of civilization. Water systems become harder to manage. Agricultural planning weakens. Infrastructure assumptions fail. Insurance models struggle. Ecosystems lose recovery time. The atmosphere still functions according to physics. But increasingly, it may no longer behave according to the stable climatic patterns modern civilization originally evolved around. One of the most dangerous features of climate instability is how ordinary it can appear in the beginning. Reservoir levels drop gradually. Summers grow slightly hotter. Fire seasons extend a few weeks longer. Insurance costs rise incrementally. Nothing feels apocalyptic overnight. And that is exactly why large systemic change becomes so difficult for societies to emotionally recognize. Human beings evolved to respond strongly to immediate threats. Storms, earthquakes, explosions. But climate transitions often unfold slowly enough that people normalize each stage as it arrives. Scientists sometimes compare this to watching the tide rise 1 inch at a time. Each change feels manageable individually. Yet, over years and decades, the landscape itself transforms. The terrifying reality is that some of the most important climate shifts may already be happening quietly beneath daily life. Water systems weaken gradually before crisis appears. Forests accumulate stress long before visible collapse. Heat affects infrastructure long before systems fail outright. Atmospheric circulation changes slowly until extreme events suddenly emerge from the new baseline. Civilization often recognizes structural transformation only after enough systems begin failing simultaneously. And by then, adaptation becomes far more difficult than early prevention would have been. The future may not arrive with one defining catastrophe. It may arrive through thousands of small changes accumulating until societies suddenly realize the world underneath them has already become something different. One reason climate instability becomes so difficult for modern societies to confront is because the atmosphere operates on timescales completely different from politics. Governments change every few years. Economic priorities shift constantly. Public attention moves rapidly from one crisis to another. But drought does not care about election cycles. Reservoirs do not recover because headlines change. Forests do not regain moisture because public attention moves elsewhere. The climate system continues evolving slowly, continuously, and without pause. Scientists increasingly warn that the current southwestern megadrought may persist long enough to outlive multiple political generations. And this creates a dangerous mismatch between environmental reality and institutional response. Long-term water infrastructure requires decades of planning. Forest restoration requires decades. Agricultural adaptation requires decades. Yet modern societies often struggle to maintain consistent long-term strategies beyond short-term political cycles. The terrifying part is that environmental systems compound over time whether civilization responds consistently or not. Every additional hot year stresses forests further. Every dry winter weakens snowpack recovery. Every severe fire season leaves ecosystems more vulnerable for the next one. The atmosphere keeps moving forward continuously, while human systems often react only after damage becomes visible. And tonight, researchers quietly fear that by the time societies fully recognize the scale of the transformation unfolding across North America, Many of the systems under stress may already be far more difficult to stabilize than they appear today. Perhaps the most unsettling aspect of modern climate science is not what researchers know. It is what they still cannot predict with complete confidence. Earth's climate system is extraordinarily complex. Oceans interact with the atmosphere. Forests influence rainfall. Ice affects planetary reflectivity. Clouds alter heat balance. Small shifts in one system can ripple outward into countless others. Scientists understand many of the major mechanisms driving warming extremely well. But the precise speed, intensity, and interaction of future climate feedback loops remain areas of active research. This uncertainty itself creates danger. Not because scientists know nothing, but because nonlinear systems can change very slowly until thresholds suddenly accelerate. A reservoir may decline gradually for years before approaching critical shortage. Forests may weaken silently before rapid collapse. Atmospheric circulation may appear stable until blocking patterns begin persisting more frequently. The terrifying reality is that uncertainty cuts both directions. Some projected impacts may unfold slower than expected. Others may arrive much faster. And because modern civilization depends heavily on stable assumptions about water, agriculture, infrastructure, and weather predictability, even moderate uncertainty creates enormous planning challenges. Scientists continue refining climate models every year. Data improves constantly. But the atmosphere is now entering conditions humanity has never previously measured within the lifespan of industrial civilization itself. Which means part of the future remains unwritten. The drought is real. The warming is measurable. The forests are drying. The oceans are heating. But exactly how these systems will interact over the coming decades is one of the largest scientific questions humanity has ever faced. For most of recorded American history, the western United States existed within a climate system stable enough for reservoirs to refill, and agriculture to expand across massive regions of the continent. Droughts came and went, but the baseline remained relatively recognizable. Scientists increasingly fear that baseline itself may now be shifting. Not temporarily, but structurally. A growing number of climate researchers now describe parts of the American West as potentially entering a new long-term climate state defined by hotter temperatures, reduced snowpack, prolonged drought stress, larger wildfire seasons, and increasing atmospheric instability. The terrifying part is that climate states do not announce themselves dramatically at first. They emerge gradually through patterns that become harder and harder to reverse. Rivers carry less water over decades. Forest recovery weakens slowly. Heat waves expand incrementally. Eventually, entire systems begin behaving differently than they once did historically. And once ecosystems and atmospheric circulation patterns adapt to a new baseline, returning to previous conditions becomes extremely difficult. The West still resembles the landscapes modern America inherited. Mountains still hold snow. Forests still stand. Reservoirs still contain water. But beneath the surface, scientists increasingly believe the region may already be transitioning into environmental conditions fundamentally different from those that shaped the 20th century itself. For years, much of the public conversation around climate focused on debate. Is warming real? Are droughts connected? Are the fires unusual? But inside the scientific community, the discussion has increasingly moved beyond those questions. The atmosphere is warming. The oceans are heating. The Arctic is melting. Fire seasons are expanding. These measurements are no longer theoretical projections. They are observational realities already visible across the planet. The real question scientists now ask is different. How far will these systems shift? How quickly will societies adapt? Which ecosystems will remain resilient, and which may cross irreversible thresholds? The terrifying reality is that modern civilization developed during one of the most environmentally stable periods in human history. Agriculture flourished under predictable seasons. Water systems relied on relatively stable snowpack. Infrastructure was engineered around historical weather patterns. But history itself may no longer fully describe the future climate now forming around us. And tonight, perhaps the most unsettling realization of all is this. The worst drought in modern American history may not have been the disaster people will remember most. It may only be remembered as the moment the atmosphere first revealed that something much larger had already begun. Modern civilization often feels permanent. Cities glow through the night. Water flows from taps instantly. Food arrives continuously. Electricity powers entire continents without pause. These systems feel stable because for most of modern history, the environmental foundations beneath them remained relatively stable too. But tonight, scientists increasingly warn that many of the assumptions modern civilization depends upon were built for an atmosphere that may no longer fully exist. The 20th century, the era during which most modern infrastructure expanded, was unusually climatically stable compared to many periods in Earth's longer history. Reservoir systems were designed around predictable snowpack. Agriculture depended on recognizable growing seasons. Power grids assumed historical heat ranges. Insurance systems relied on historical disaster probabilities. Entire economic models quietly assumed the past would remain a reliable guide for the future. But across North America, those assumptions are beginning to weaken simultaneously. The atmosphere is becoming hotter, drier in some regions, wetter in others, and increasingly unstable overall. Fire seasons lengthen. Heat domes persist longer. Atmospheric blocking patterns stall. Water systems fluctuate more violently. The terrifying part is not simply that disasters are increasing. It is that multiple environmental systems are now drifting outside the historical ranges modern societies originally optimized themselves around. Civilization can adapt. Humans are extraordinarily adaptable creatures. But that adaptation requires time, resources, coordination, and stable institutions. And the climate system is now moving continuously whether societies feel prepared or not. The roads still function tonight. The lights still remain on. The cities still operate. Yet underneath the surface, modern civilization may already be entering environmental conditions fundamentally different from those that allowed it to rise in the first place. And so tonight, after traveling through collapsing snowpack, stalled jet streams, atmospheric thirst, megafires, weakening forests, groundwater depletion, heat domes, smoke-filled skies, and the hidden instability spreading through the climate system itself, we arrive at the most unsettling conclusion of all. The drought was never the full story. The drought was only the first visible signal that something much larger had begun shifting across the atmosphere of North America. Because what scientists increasingly fear is not a disaster, but a long transition toward a more unstable planetary system overall. A world where heat lasts longer, fires grow larger, water becomes less predictable, ecosystems recover more slowly, and the atmosphere itself behaves less like the stable climate modern civilization inherited, more like a system entering unfamiliar territory. The terrifying reality is that many of these changes are no longer distant possibilities waiting somewhere in the future. They are already measurable now. Reservoirs are declining. Forests are stressed. Oceans are warming. Fire seasons are expanding. Atmospheric patterns are shifting. The system is already moving. And yet perhaps the strangest part of all is how quiet this transformation can feel while it unfolds. Most nights still look normal. Highways remain full. Cities still glow beneath the stars. Daily life continues. Civilization adapts one season at a time. But slowly, almost invisibly, the boundaries defining what once felt normal begin drifting further and further away. The atmosphere remembers every imbalance, every wildfire, every degree of warming, every disappearing glacier, every drying forest. And over time, those accumulated changes begin reshaping the future itself. Still, within all of this uncertainty, one truth remains deeply human. Civilization has faced environmental change before. Societies adapt. Technologies evolve. Knowledge expands. The future is not fully written yet, but understanding the system matters. Because the first step towards surviving any transformation is recognizing that the transformation has already begun. And tonight, the atmosphere above North America may already be telling that story more clearly than ever before. And now, as the night settles quietly across the continent, the atmosphere continues moving above mountains, deserts, forests, rivers, and cities exactly as it always has. Winds still circle the planet. Oceans still exchange heat with the sky. Clouds still gather beyond distant horizons. But something inside the balance is changing. Slowly, relentlessly, almost invisibly. The drought was never just about missing rain. It was about the atmosphere itself beginning to behave differently. Hotter, thirstier, more unstable. And tonight, scientists across the world continue watching these patterns carefully, because what happens next may shape the future of entire civilizations for generations to come. Yet despite all of this uncertainty, there is still something strangely calming about understanding the system. Because fear often grows most powerful in darkness and confusion. And knowledge, even unsettling knowledge, allows us to see the larger picture unfolding around us. So as you drift deeper into sleep tonight, imagine the immense climate engine of Earth turning silently through space. Jet streams flowing high above the continents, heat rising from the oceans, snow melting quietly in distant mountains, forests breathing beneath the stars. An entire planetary system in motion, connected in ways humanity is only beginning to fully understand. And perhaps the most important realization of all is this: the atmosphere does not change in a single moment. It changes gradually, season by season, year by year, until eventually humanity realizes the world it once considered permanent has already become something new. Thank you for joining me tonight on Discover the Universe Before Sleep. And if this journey through the terrifying signs of America's growing megadrought helped you relax, think deeply, or simply understand our changing planet a little more clearly, consider subscribing and quietly supporting the channel so more people can continue exploring the mysteries of Earth, space, climate, and the universe before sleep. Until next time, stay curious, stay thoughtful, and let the universe carry you gently into the night.